Welcome back. Today is about linear algebra. I think it's our last algebra topic before the remaining topics about computer science in this course. Last time I taught this lecture last year, I don't think it went that well. And when I went to revise it, though, this year, I was like, well, it looks okay to me. So I'm just going to try it again. We'll see how it goes. And if you guinea pigs don't like it this time, I guess we'll do something for the next year's batch. Okay, linear algebra. This is going to be an important topic, by the way, for our next two lectures about random walks and quantum computation. Okay, so in a nutshell, linear algebra is about vectors. I hope you've seen vectors before, but basically they look like this, at least concretely. They're like lists of numbers arranged like that. And the number of numbers in this list, this vector m, is called the dimension of the vector. In linear algebra, though, we don't call the numbers numbers, we call them scalars, because, I don't know, they can be used to scale vectors, so you'll need to get used to that. And in fact, the scalars can be from any field, so that was another reason we talked about fields a few lectures ago. It's also important for linear algebra. Okay, so you fix any field, and then vectors, in this case, would be a list of numbers from that field. And it's particularly nice if the field is like the real numbers, and if the dimension is at most 3, because then you can draw pictures in space. It doesn't work so well with other fields or higher dimensions. Okay, so this is my, I'm not so good at drawing anyway, but this is my interpretation of R3. Okay, three-dimensional space. So this is the vector 7, 5, 2. And, you know, here's 7, 5, 2. And, like, here's a picture of the vector. You know, it's like an arrow from the origin to this point, 7, 5, 2. Hello. Okay, so that's a vector. Now we come to the linear algebra part. The key operation on vectors that we will see is taking linear combinations of them. Okay, so what is a linear combination? It means adding vectors and also simultaneously scaling them, which multiplying them by scalars. Okay? I'll give you some examples. So here are three vectors, 3, 2, 1, 4, 3, 1, and this one, which I won't read. And a linear combination is you multiply each one by some scalar. This is all over the field real numbers. And you add everything up. Okay, and that happens component-wise. So in the first coordinate here, we get 2 times 3 plus 1 times 4 plus 2 times minus 1.5, which is 7. Okay, so we scale each of these vectors and then add them up to get this last one. Okay, so this has a geometric meaning too, at least in the case where the field is the real numbers. So now I'll dial it down to 2 dimensions. This is R2. And let me imagine two vectors, which I'll call u and v. So here they are here. Okay, so the first operation in linear combinations is scaling. So this is when you just multiply a vector by a number. So this is a picture of 1.5 times u. So, okay, so it just stretches it. You know, if the number is less than 1 over the reals, then you're sort of shrinking it. This would be maybe 0.7 times v. And now I'm going to add these two up. And, you know, like the head-to-tail rule for adding vectors, right? So, I mean, the sum of these two yellow guys is this diagonal of the parallelogram. Okay, so this is a, you know, full-on example of a linear combination. This vector here is 1.5 times u plus 0.7 times v. Okay, I'll do another example. So this is also a scaling of v. It's negative v. It's just the reflection of v. And I guess this would be 1.5 times u plus negative v. Okay, we take this vector and put it over here. I assume you guys have seen this before, but it's a good warm-up. Okay, so that's linear combinations. I should say that, you know, I draw these pictures when the field is the real numbers, and you can do that and have geometry when the field is the real numbers, but we're going to talk about the case where the field is not the real numbers. Maybe it's a finite field, like the set of numbers mod 11. Then your vectors, you know, are lists of, in this case, f11 to the 3 are lists of 3 numbers mod 11. And, you know, even though you can't really draw the same pictures, some of the intuition you get from the geometry in the real case can be helpful. Okay, let's say a little bit more about linear combinations. So say we have two vectors, 3, 2, 1 and 4, 3, 1. Here's how you can, you know, sort of notationally take linear combinations of them. If you want to take linear combinations of, say, two vectors, make them the columns of a matrix. Okay, I'm not sure if you've seen matrices before, but it's like a box with numbers in it. So this is stacking these two vectors in a row as a matrix. Okay, and then a linear combination of these two vectors with multipliers a and b, that's what we were writing before, and this is another notation for it. Okay, so this sort of combination, it's really a matrix times a vector, means a times the first row plus b times the second. Sorry, a times the first column plus b times the second column. Okay. All right, so that's the linear combination I just wrote. And you can take this, extend it to like any number of dimensions as the definition of what it means to multiply a matrix by a vector. Okay, it's taking linear combinations of the columns. Now, if you want to do like a bunch of linear combinations, a bunch of different linear combinations of the same, let's say, two column vectors, then just like stack all the a's and b's you want together also in a row to make a matrix. Okay, so here I have 4 different linear combinations of these two vectors, 3, 2, 1, and 4, 3, 1. And what you get with each of the different combinations is given here. And this is also the definition of matrix times matrix multiplication. Okay? Probably you also know the formula, right? You sort of do like this. It's the same thing. You do like this row dot this column to get this entry, this row dot this column to get this entry, and so forth. But you can also think of it in this case as taking like 4 different linear combinations of the columns. Okay. Is there a question about that? Okay. So you all know how to multiply matrices? All right. Great. Okay. I'll remark that multiplying matrices is associative. It doesn't matter where you put the parentheses, but it's not commutative. Okay. So multiplying matrices, you can't do it in the opposite order necessarily. In particular, the dimensions have to add up. You can't match up. You can't multiply this one on the left times this one. Okay, so one more thing about linear combinations. You see, if you fix this, 2 vectors, let's say, and we imagine taking different linear combinations of it, then for every 2 numbers, a and b, you get like a resulting vector in R3. So you can really think of this thing as a map that maps pairs of real numbers to triples of real numbers. Okay, it's a map that maps R2 into R3. Okay, so for example, 1, 0 maps into 3, 2, 1, 0, 1 maps into 4, 3, 1. 1, 1 maps into the sum of the 2 column vectors, 7, 5, 2. Okay, let's do some application to keep us entertained. The Fibonacci sequence. Okay, so this is the Fibonacci sequence. It's like each number is the sum of the previous 2 numbers, and it starts with 0, 1 usually. Okay, and you see, to get the next number in the sequence, you only need to know the last 2. Okay, so sort of the next number is a function of the last 2. So I might ask, if I stacked things into little height 2 vectors, if I have the k minus 1 entry and the k minus 2 entry, how could I sort of go to the k entry and the k minus 1 entry? This is a map from R2 into R2. And in fact, you can represent it by this matrix vector multiplication. I claim this is true. All right, it's just saying that to get fk, you take fk minus 1 plus fk minus 2, and fk minus 1 is just 1 times fk minus 1 plus 0 times fk minus 2. Okay, so does everybody agree that if I put the k minus 1 and k minus 2 ones here and multiply it by this matrix, I'll get the next 2? I'll show you the picture here. So the first 2 are 0 and 1, and if I multiply by this fixed matrix, 1, 1, 1, 0, I get the next 2, 1, 1. Not the next 2, but like the first and the second. Okay, if I do it again, I get 1 and 2. If I do it again to 2, 1, I get 3 and 2, and 5 and 3. I think you know these numbers, right? 8 and 5. Okay, and at this point, for example, I've multiplied 1, 0, the initial 2 numbers, I think 5 times by this matrix. So, this last step is like this matrix raised to the 5th power applied to the first 2 numbers gives you like the 4th and the 5th. Got that? Okay, that's all well and good. And in general, we have this relationship. If I do it if I multiply by this matrix k times, I'll get the k plus first number and the kth Fibonacci number. Okay, So where am I going with this? You know, as I said before, this matrix, this 2 by 2 matrix, you can think of it as a map that maps two-dimensional vectors into other two-dimensional vectors. And when you start up, you know, when you apply it to things that are already like 2 consecutive Fibonacci's, you get the next 2 consecutive Fibonacci's. But in general, I mean, it maps, you know, you can give it any vector in R2, and it'll give you some other vector in R2. So what does this map really look like? Okay, this is a good job for the computer. So let me use technology. This is MATLAB. It's a good program to use if you have matrices or vectors. So the matrix was 1, 1, 1, 0. I don't know if you can see this, but you'll see something in a second. So MATLAB gives me this thing that lets me play around. Okay, so this is showing the green vector x, which is currently 1, 0. And if you multiply it by a, you get, we already know, 1, 1, which is the blue vector. All right? So now I'm going to get to change the green vector in x, and it'll show me what ax becomes. For some reason, it only lets you do x on a circle. So I'll do it on a circle. So if I move x a little bit up, like this, you see ax moves a little bit. Okay, so if that new green thing is x, that's the new value of a times x. So I'll move it a little bit more. See if I keep going. Now here actually something interesting happens. This is some vector, I'm not sure what it is, but you see that for this vector, when you multiply by ax, when you multiply by a, it just gets longer. It doesn't change its direction. So that's like an interesting thing. A just scales this particular vector. Okay, so I'll keep going. Goes like this. Okay, now actually something interesting happens too. For this vector x, ax actually also is just a scaling of x. It looks like it's the opposite, right? But it's just like negative something small times x. Okay, so a also just scales this vector x. Okay, and I can keep going. It looks like this. That's similar. Okay, etc. Okay, so for example, if it was x is 0, 1, then we saw that ax would be 1, 0, and so forth. Okay, so actually in this picture, I want to highlight those 2 examples I said. There's sort of 2 interesting directions. This one, which a just scales, and also this one, which a just scales. This one is by a negative amount. Is that clear? So let me investigate that further. Okay, that was the picture we just had. Okay, so those are the 2 interesting directions. They're like the axes of this ellipse. Is there a question? Somebody's just like pointing. It's sang. Did you notice something awesome on the ceiling? Okay. All right. Okay, so what do I mean? You know, these are 2 interesting directions. If we represent this direction that I found interesting by x, y, then it means that this matrix times that vector is just some scalar multiple of that vector. Okay, and if you look back in one case, like it was kind of stretching it by about 60%, and the other case it was like shrinking it by some 40% and also negating it. So these lambdas were around this amount. Now actually I want to solve. I mean, I want to just use some algebra to find out what these 2 special vectors are. So it'll be interesting. And you see, it doesn't really matter if I scale the vector itself. It'll still be scaled by the same amount, which is to say, we can assume without loss of generality that, let's say, y is 1. This is not that important. But let me assume that for these special 2 vectors, y is 1. Okay, so then I would be like solving these equations. If I multiply this out, I really get 2 equations, you see. The first equation is like x plus 1 equals lambda x. If I do this times this equals this. And the second equation is just x equals lambda. People see how this matrix vector multiplication, this equality turns into these equations? Okay, so these are easy to solve. I mean, it tells us that x equals lambda, so I could plug in x here and get x squared equals x plus 1. So I get this. Okay, and this is some quadratic equation, x squared minus x minus 1 equals 0, which you can just solve with the quadratic formula. And it's this. Okay, I guess you guys all know how to do the quadratic formula. So this actually tells me these 2 specific vectors. It looks a little bit ugly. which have the property that A just scales those vectors. And this lambda tells you the amount that it scales them. Okay, so this is, there's two solutions here, one plus or minus root 5 over 2. So let me call phi the bigger solution, which is about 1.6, and psi the smaller solution, which is like minus 0.6. Okay, and what we just saw was that my battery is dying. What we just saw is that the vector psi or phi1 has the property that when you hit it with this matrix, it gets multiplied by psi or phi. And similarly for the vector phi comma, man, I'm getting them backwards, psi comma 1, it gets scaled by this negative 0.6 when you hit it. Okay? And so that's very cool because, with the Fibonacci, we were interested in multiplying this matrix many, many times. And this equation just says, if you multiply this particular vector by 1, 1, 1, 0, you just, scale it by a factor 1.6. If you just do it many times, it'll just get longer and longer and longer in that same direction. Okay, so you can easily see that this matrix, the power of k times this vector, gives you the same vector back scaled by phi to the k. And similarly for psi. Okay? It looks a little mysterious. You'll see where I'm going with this soon enough. But any questions about this? All right, so what I'm saying is these two vectors, this is phi comma 1, this is about 1.6, and this is about minus 0.6. All right? These are the two vectors that get just stretched by A. Okay, but now if we go back to Fibonacci, we didn't really care about these weirdo vectors, right? We were interested in what happens when you repeatedly multiply A against the starting vector, 1, 0, right? Which is this red vector. So we know a lot about how A acts on these two vectors, but we kind of care about how it acts on this vector. Can somebody suggest something that we can do to use our knowledge about how A acts on these vectors to get knowledge about how it acts on the red vector? Yes? Yeah, good suggestion. The suggestion was to express this red vector as a linear combination of these two interesting vectors. And actually, you see if you subtract this vector from this vector, you almost get the red vector. You get something that's going in exactly the right direction. It's just that this difference is like root 5. Okay, so if you were to just divide this whole equation by root 5, you'd get that 1 over root 5 times this minus 1 over root 5 times that equals the red vector, 1, 0. Okay, so I think that's what I just said. Yeah, so 1, 0 is this linear combination of the two vectors. Okay, so now let's go back to the Fibonacci observation. If we want to get the k plus first and the kth, we know that you get it by multiplying the initial two, 1, 0, by a raised to the power of k. And we just decided that 1, 0 can be written like this in terms of the two special vectors. That's this linear combination. And we know when you multiply this matrix against psi 1, you just get the same vector again times psi to the power of k. And similarly for, sorry, that's phi. Similarly for psi. Okay, and that's great because now if you just, we did a lot of calculations here, but just look at this equality from here to here. And in particular, look at the second coordinate. We get f sub k, my battery lives, equals, here we just have 1, so I get phi to the k over root 5 minus psi to the k over root 5. Okay, which is exactly this formula. Okay, so this is the punchline. This gives us an explicit formula. It's this number to the k over root 5 minus this other number to the k over root 5 for the kth Fibonacci number using the power of linear algebra. Okay, any questions about that? Okay, so now you can compute the kth one without computing all the intermediate ones. You just need to punch this expression into your calculator. Okay, so let's talk a little bit more about the theory of linear algebra. So the key step there was, we had these interesting two vectors, and we wanted to express this other vector we cared about, 1, 0, as a linear combination of them. So let's look more generally about this sort of expressibility problem. When can you write one vector as a linear combination of some other vectors? Okay, so here's R3, and here's some vector 7, 5, 2. Okay, so is it true that all vectors in R3 are linear combinations of this vector? I see you shaking your head. What vectors do you get if you take all the linear combinations?
Anything that spans that line?
Yeah, I mean, you can't add anything up. You just get to scale this vector. So the only thing you get is just this line through the origin. Okay, I'll give you another vector, 3, 4, 1, which is out here. So what do I get if I take all linear combinations of these two vectors? Yes? Yeah, if you haven't seen it before, maybe it's not so geometrically clear, but if you imagine the plane that contains the two of them, you can never escape that plane by adding up scalings of these two vectors. Okay, so you just get all vectors in this two-dimensional plane. Okay, what if I give you one more vector? Do you get, when I allow you to use linear combinations with that, do you get all of R3? Yes, it depends. On what? Yeah, you guys are good at linear algebra. Maybe it doesn't matter how good my lecture is. Yeah. I mean, if you take another vector that's already in the plane, you're not going to get anything more. But if you take anything outside the plane, then by taking appropriate linear combinations with it, you can get everything in space. Great. Okay, so then let's make some definitions. If I have a set of vectors, v1 through vn, then the span just means all linear combinations of them. And another definition is that a set of vectors is called linearly independent if none is in the span of the others. Okay. Okay, so in R3, if you take two linearly independent vectors, that basically just means they're not parallel, then their span, all the linear combinations, is some 2D plane through the origin. And a 2D plane is kind of like a copy of R2, right? It looks like R2, just sitting in three-dimensional space. So let's make these sort of notions a bit more formal. So, originally I told you concretely a vector was like a list of numbers. Well, that's sort of the concrete version, but now I'll give you the full general version of what is a vector space, okay? In the style of our definitions of what is a field and what is a group and so forth. Okay, so the first thing you need to do is fix a field for your scalars. And then a vector space over this field is a set V, which means all the vectors, with two operations, addition of vectors and multiplication of vector by a scalar, which gives you a vector back. And you need two properties. First, vectors together with addition should be an abelian group, okay, which basically means you can add and subtract, and addition is commutative. And as for how scalars interact with vectors, they should interact in the way you expect. So there should be a distribution of the scalar multiplication with addition, and these other obvious properties. So I'll give you some examples of vector spaces. Some will be familiar. Some will be kind of weird, but if you examine these slides at your leisure, you'll see that indeed they satisfy all these properties. Okay, so R3 is a vector space, and the field is R. Okay, you can add and subtract vectors in R3 and multiply them by scalars from R. More generally, we have n-dimensional space. Actually, more generally, if f is any field, you can look at f to the n, which means all tuples of n scalars. And this is a vector space. You can add and subtract these tuples, and you can scale them by field elements. For example, f2 to the 7 is a vector space with 128 different vectors in it. Okay, all 7 tuples of zeros and ones. Okay, and as I said before, when the field is the reals, you have this geometric intuition that doesn't exactly hold up when you're working with finite fields, but all the definitions are still okay. So here are two vectors in f2 to the 7, and here's a linear combination of them. You see that the addition takes place and the multiplication take place in the field with two elements. The number is mod 2. Does it make sense? Any question about that? Okay. I'll get into slightly weirder examples. Remember, this is our notation, f of x, for all the polynomials with variable x and the coefficients from the field f. And I claim this is a vector space. It doesn't seem so obvious because it's not just like tuples of numbers. But still, you have the property that if you have two polynomials, you can add them, and addition is commutative. And you can multiply a polynomial by another field element. And all the arithmetic interacts in the way you expect, so this is also a vector space. Okay, so these are some important vector spaces. I'll tell you a few more that probably won't really come up but in 251, but just to give you examples of other weird ones you can tell your friends about. The set of real numbers is a vector space with the field being Q. This means that you can add and subtract real numbers, and you can multiply any real number by a scalar from Q, and you'll get some other real number. That's kind of a strange example, but you see it fits. The set of all functions, like in calculus, from the real line to the real line, is also a vector space with the field being the real numbers, because you can actually add two functions together. You can multiply a function to scale it vertically. So it counts as a vector space. And a similar example that I only put up because it's like my personal favorite vector space that I love in my life is the set of all functions from this vector space to the real numbers. So I'm not going to belabor this point, but I couldn't resist telling you my favorite vector space. Okay, but these ones, in particular also the polynomial ones, are more the familiar ones that we'll expect you to know about. Any questions? Yeah.
Why is it your favorite vector space?
Oh, because well, my favorite object is the Boolean function, right? Which maps, n bits to 1 bit. So that would be functions mapping, f2, that's 0, 1 to the n, into f2. But to really study it, these Boolean functions, like I love, you need to use some kind of Fourier analysis. And then you need to allow them to map into the reals to make all the math work out. So thank you for asking. Any other questions? Okay. All right, so I'm going to give you a few more formal definitions, and then we'll get to some applications. Yeah. Okay, so I talked about linear combinations before, but now we're in the setting of an abstract vector space. So just to sort of repeat the definition, if you have n vectors in some vector space V, and you have n scalars in some, the associated field F, then this is a linear combination. A1 times V1 plus A2 times V2 plus up to AN times Vn. Okay, and given a set of vectors S, to extend this definition span, we write span of S to, again, mean the set of all the linear combinations you can get from them. And I'll bring this up to, the empty sum counts as 0. So for the technically minded among you, if I say span of the empty set, that means the set whose only element is the 0 vector. Okay, and whenever you have a set of the form, span of some vectors, we call that a subspace. Okay, and it's similar to, if you remember this notion of subgroup, a subspace just means like a collection of vectors which itself forms a vector space, essentially which means a set of vectors W closed under taking linear combinations. So whenever you take linear combinations of stuff in W, you only stay in W. Okay, it's like a plane in R3. If you take linear combinations of vectors from a plane, you only stay inside that plane. Okay, so let's do some examples. Okay, let's consider this vector space. It's like Rn, except it's f2 to the n. So it's all the tuples of n elements from the field 0 and 1. The integer is mod 2. So here's a set of vectors. Take all the vectors in this space which have an even number of ones. I claim that this is a subspace. And we'll see it in two ways. One way to see it is to show that it's closed under linear combinations. That whenever you take some vectors in this set, E, and do linear combinations, you get something that's still in E. Now, linear combinations, when the field is F2, are very simple because there's only two scalars, 0 and 1. And like 0 is pointless. So really, linear combination, when the field is F2, just means adding some stuff together. OK, so can somebody tell me why if U and V are vectors in this set E, their sum is also in E? Yeah? Yep. Yes, that's right. Yeah. So you see, if U had some number of, an even number of 1s, and V had some even number of 1s, then like together there's still an even number of 1s. And then, as Thompson was saying, like if you actually add them mod 2, right, the only thing that can happen is like pairs of 1s can cancel out. So maybe you'll cancel out some further even numbers of 1s, but you'll still be left with an even number of 1s. OK, so that proves that this is a subspace. OK, and it's a bit different from the sort of, hyperplanes that you imagine when you're thinking about, let's say, Rn or R3. Here's another way to see it. I claim that E, the other characterization we have of a subspace is that it's the span of some vectors. So I claim that E is the span of these n minus 1 vectors. Can somebody tell me why? Yeah?
Because you can write any vector of F1 as a combination of those ones just by picking if it has a 1 in any of the first n minus 1 spots, you include that vector.
Yeah, that's more or less right. Yeah, I won't completely prove it, but on one hand, OK, what is a linear combination? It's adding these vectors up with scalar multiples. But as I said, the scalars are just 0 and 1. So it really just means adding up a subset of them. And when you add up some subset of these, what goes on, right? Basically, there's no interaction in the n minus 1 columns. You can sort of get any first n minus 1 bits you want. But then this last bit is cooked up, right, so that it sort of makes sure that you always have an even number in your sum. All right? So if you add up like an odd number, this last bit will turn into 1 and make the total sum even. If you add up an even number of columns, this last bit will turn into 0, which will keep the sum even. OK, I'll let you think about that a little bit more when you look at the slides. OK, let me do an example where it's more familiar geometrically, R3. So let's let U, V, and W be these three vectors. What is the span of these three vectors? Can somebody describe the set of vectors that are spanned by these three? Yeah? Yep, exactly right. So if you take real linear combinations, it's pretty easy to see you can get anything you want in the first two coordinates, but you'll always get 0 in the third coordinate. OK, so that's the span. OK, so there's the three vectors, and you see they're all sitting on this z equals 0 plane. So their span is just that subspace. In fact, you see here the spanning set is a bit redundant. If you only want to sort of get all these vectors in this plane, you don't really need all three of these vectors to achieve it. Yes, that's right. Any two of them would have worked. OK, because actually, pictorially, any two of them have the property that they sort of pictorially span this plane on the ground. OK, so you usually prefer sort of like an irredundant set for your spans. OK, and that leads us to the formal definition of what linearly independent means. OK, if you have a set of vectors S, and think of this as spanning some subspace, we say they're linearly independent if no one of those vectors in the span of the rest of them. OK, because if you have a vector that's like in the span of the rest of them, then it's kind of redundant for the purposes of taking linear combinations. Okay, so in this example with these three vectors, u, v, and w are not linearly independent. The term for that is linearly dependent. And it's because, for example, w is a linear combination of u and v. Right? W is actually just the sum of u and v. Okay, what about u and w? Are they linearly independent? Yes. There's no way, I mean, if it's just u and w, there's no way to like write w as a linear combination of u, or vice versa. Okay, and actually any pair of them is linearly independent. What about just the singleton set u? Is that linearly independent or dependent? Anybody? Okay, just say it out loud then, yes or no. Yes, it's linearly independent. You cannot write u as a linear combination of nothing. Okay, now I'll give you the two edge cases. 0 is actually not linearly independent because 0 is in the span of the empty set. Because I told you as a technicality, the span of the empty set is 0, and the empty collection is linearly independent if you parse through all the quantifiers. Anyway, these are like edge cases, so I won't break your brain on those. Okay, any questions about linear independence? Okay, it's like a set of vectors that are sort of not redundant for the purposes of spanning. Okay, so suppose we have some vectors S1 through Sn now, and they're linearly independent. And we look at their span, okay, which is the set of all linear combinations of them. Call that W. This is an important theorem. It says that every vector in the span is a unique linear combination of the vectors in S. Okay, so once you have, this is sort of capturing the fact that these linearly independent vectors are sort of irredundant. There's only like one way you can use them to make a linear combination to get a given vector. Okay, so this theorem is pretty easy to prove, so I will prove it. Let's say you have some vector v, and there's two different ways to write it as a linear combination of S1 through Sn. Say this linear combination with scalars A and linear combination with scalars B. Okay, what should be the next step in the proof? Yeah, subtract them. Okay, so our task, to show that it's unique, we want to show that A1 equals B1 and A2 equals B2 and so forth. So suppose for a contradiction that's not the case, say some AK differs from some BK. And let me just assume without loss of generality that it's A1 that's different from B1. Okay, now I'll subtract them. And when I subtract them, I get this. I get V minus V, that's 0. And then I get this linear combination of S1 through Sn. But we're assuming now that A1 and B1 are different. These are field elements, remember. They're scalars. So this subtraction, A1 minus B1, is not 0. So I can rearrange this equation. I can put all this junk on this side and then divide by A1 minus B1, okay, because it's not 0. So you're allowed to divide by it. And what happens is now I've written S1 as some linear combination, these are scalars, of S2 through Sn. Okay, and that contradicts the assumption that S1 through Sn are linearly independent. Remember, linearly independent means you can't write one of the vectors as a linear combination of the others. Okay, any questions about that? Okay, when this happens, when you have a subspace like W, the span of some stuff, and furthermore, the spanning set is linearly independent, we call it a basis for the subspace. Okay, and this theorem says that when you have a basis for a subspace, every vector in the subspace can be written as a unique linear combination of the basis vectors. Okay. This is a super technical note. From now on, I'm only going to talk about vector spaces with finite bases. Probably for the rest of the course, even. Well, that's not quite true. Anyway. Now, there's really one first non-trivial theorem in linear algebra, which I will tell you now. It's this. This will be our last sort of theoretical theorem, and then we're going to move on to applications. So the theorem says if V is a vector space, then every basis of V has the same number of vectors. This is something you kind of have come to expect, right? When you think about like, R2 or R3, there are many different bases in R2, pairs of vectors that are linearly independent and span everything. But it's always two of them, right? You cannot have a basis of size 3 or of size 1. And that's true in general. So whenever you have a vector space, every basis has the same number of vectors. It's called the dimension of the vector space. Okay, and we're going to do the proof. So proof actually takes a full 1.5 slides, maybe 2 slides. Okay, so actually, this is the statement I'm going to prove. That if you have a linearly independent set called L, and a spanning set for V called S, then the cardinality of L is at most the cardinality of S. So a spanning set always has at least as many vectors as a linearly independent set. Now this is the theorem that I actually want to prove. So why does this statement allow us to deduce this theorem? Yeah? No, I mean S is spanning for V. No. So it's a good question. So in this, let's take it back a step. In this proof, L and S kind of have nothing to do with each other. I have one vector space V, and I'm trying to show that whenever I have a basis for V, it has some fixed, number of vectors. It can't be more or less. I'm going to prove that by proving this statement as kind of a lemma. And in this lemma, I'm going to say let L be any linearly independent set. It could have fewer vectors than the dimension that we're going to know exists. Maybe it only has 2 or 3 vectors. On the other hand, I'm going to let S be any spanning set. The only restriction I have is that every vector in V is in the span of S. So S could actually have way more vectors than the dimension that we're going to prove exists of V. Okay, but just whenever you have a spanning set, think about Rn. Whenever you have a spanning set, you need to have at least n vectors, if you know a little bit of linear algebra already. And whenever you have linearly independent vectors in Rn, you have at most n of them. Okay, and in fact, that common number that you can have both linearly independent vectors of this cardinality and a spanning set of this cardinality is the dimension. Okay, so that's a good point. I'm going to prove this, but any questions about what exactly we're proving here? Okay, so let me ask this question again. Suppose I prove this. Why does it show that every basis has the same number of vectors? I'll remind you what a basis is. It's a set of vectors that spans the space and is linearly independent. Yeah. That's right. So here's how to deduce the theorem from this statement. Suppose T1 and T2 are both bases. We want to show that they have the same size. That will prove this. Well, they're both linearly independent and they're both spanning by definition. So you can apply this sort of lemma twice. You can use it to show that T1 is at most the size of T2 and also T2 is at most the size of T1. So they have to have the same size. Okay, so here's the claim that we're trying to prove. I'm going to go through this a little bit fast because it's somewhat boring and you may be used to it already. But if it goes too fast, then look at the lecture slides when we're done. Okay, so it's going to actually be the proof is sort of like an algorithm, which changes which vectors are in the set L and which vectors are in the set S. So I'm going to say, take any vector called L1 in the set L and delete it. And furthermore, L1 is a linear combination of the vectors in S. Why is that? I don't know who said that, but I don't think it was correct. Why is L1 a linear combination of the vectors in S? Yeah. That's right. S is a spanning set, so everything is a linear combination of stuff in S. And it's also non-zero because you can't have any zero vectors in a linearly independent set. It's a minor point. Okay, so that means we can write L1 as some linear combination of the vectors in S. I call the vectors in S S1 through Sn. Now, since L1 is not the zero vector, it means not all of these A's can be zero. So let's say without loss of generality that the first A is non-zero. So now look at this equation. We could take all this junk to the other side and divide by A1. And what we'd get is that S1 is a linear combination of L1 and S2 through Sn. And so what this proves is that if we redefine S to not have S1 in it anymore, but to have L1 instead, that would still be a spanning set for V. Because before S with S1 through Sn spanned everything. Everything was a linear combination of S1 through Sn. But I just showed, like, whenever you have S1, you can write it as a linear combination of L1 and S2 through Sn. Okay, so instead of having S1, you could instead have L1, and you'd still span everything. Okay, so we kind of took one guy from L, deleted it, and moved it into S. And we still maintained the fact that L is a linearly independent set, unless we got rid of everything. Well, actually, it's still a linearly independent set, and S now was still a spanning set of the same size. So I'm going to sort of repeat. I'm going to take L2, another vector from L, and delete it. And S is still a spanning set, so again, L2 is some linear combination of the vectors in it. Okay, now the vectors in it are L1, S2, up to Sn. And I claim that one of A2 through An has to be non-zero now. Because suppose all of A2 through An were 0, then we'd have L2 equals A1 times L1. And that would mean that L2 is a multiple of L1. So L2 and L1 would not be linearly independent. Okay? So without loss of generality, let's assume that A2 is non-zero. And now it's going to be sort of like before. We have this equation. A2 is non-zero. Take this junk with L1, put it on the other side. Take this junk with S3 through Sn, put it on the other side. And you can also divide by A2. And you'll get that S2 is a linear combination of L1, L2, and the rest of the S's. So again, that means, whereas before S was L1, S2, S3, up to Sn, we've just shown that S2 is some linear combination of L1 and L2, and S3 through Sn. So instead of using S2, we can use L2. And we'll still span all of V. We're almost done, but any questions to this point? This is like the most painful part of the lecture. All right. Well, basically that's it. So what we've shown is that, by using the fact that L is linearly independent, we can keep bringing some vector from L, taking it out of L, and sticking it into S in such a way that you always maintain that S is a spanning set. But we never change the number of vectors in S. It's always n. Okay, so that means, if you can keep deleting things from L and putting them into S, then L must have had at most n things to begin with. Okay, so the cardinality of L is at most the cardinality of S. Okay. So that's enough for the theory. So the last half an hour will be about some applications. Any questions? Okay. If you remember several lectures ago, we talked about error correcting codes. This was in the polynomials lecture, and we gave this very clever scheme by which Alice can send some messages to Bob over a noisy channel, meaning, even though some of the, let's say, packets or symbols got corrupted or erased, if Alice included some redundancy, she could still get her message across to Bob in a decodable way. And for example, in the application, the example we did, if you remember, Alice was sending some d plus 1 symbols over some field, maybe of size 257, to Bob, and she used polynomials. She used this Reed-Solomon, or whoever, used this Reed-Solomon code that could guard against k corruptions. And basically the idea was you treat these symbols as the coefficients of a polynomial, and then you send the polynomial's values on this many different field elements to Bob. So that looked great. I trust you remember it all. But there's sort of a problem with this, which I did not mention at the end of that lecture, and luckily nobody else mentioned. What if this number, basically the number of symbols she wants to send plus the number of corruptions is bigger than 257? I told you to send the polynomial's values on this many different points, but now there aren't that many field values. So that's a problem. So really this only works if you're sending really short messages. Another issue is it's sort of assumed that this channel, when it corrupted some symbols, that would corrupt one symbol, which is a symbol from the field of size 257, basically a byte. But what happens if you have a channel that corrupts individual bits? Then this thing doesn't work. Okay, so that's two issues. So I'm going to give you a different slant or a different idea for error correcting codes now that uses linear algebra that will, it'll solve these two issues. Okay, so let's think of the setup. Now I'm going to imagine that Alice wants to send an n-bit message to Bob. Okay, we're going to think about bits, and we're going to imagine that when it gets sent, some k of the bits can get corrupted, which basically means flipped to the opposite value. Okay, so how can Alice still get her message across by adding some redundancy? This is, again, the problem that we want to solve. This is slightly complicated, so let me start with an easy case. Let's say the channel can only flip 1 bit. You can imagine that at most 1 bit will get corrupted. And let me, for simplicity, assume that Alice wants to send an n-1 bit message. It's going to make our notation easier. Okay, we're going to solve this problem, but let's think about an easier problem. Bob doesn't have to worry about figuring out Alice's message. He just has to try to decide if there was some bit that got flipped, or if the whole message came through clear. So this is probably a problem that you know the answer to. Suppose you want to send an n-1 bit message, maybe add on some redundancy, and you kind of want to guard against the possibility that either 0 or 1 of the bits gets reversed. What's a simple thing that Alice can do so that Bob can check if there's been a corruption? I guess you're banned. Yeah? Yes. Yeah, exactly right. Just tack an extra bit on the end, which is the parity of all the message bits, or it's a parity check bit. Okay, so this is kind of a fairly well-known basic idea in computer science. She just tacks on a bit that's the parity of the message's n-1 bits. Okay, which in particular means she's always transmitting a string that has an even number of ones, no matter what her original message was. So she, only uses n bits, has an even number of ones, and now Bob can tell if there was an error in transmission, assuming he sort of promised that there'll be either 0 or 1, right? If he sees an even number of bits, he's like, great, I got it exactly. If he sees an odd number of bits, then he knows, there was a corruption somewhere. And this is pretty good. We used Alice transmitted n bits, and she was able to send 2 to the n-1 different messages, right? Because she could start with a message that was any n-1 bit string. And Bob is able to detect any 1-bit error. As you can show, this actually was a problem on the midterm last year. This is optimal. Okay, this is the most efficient way to transmit an n-1 bit message while guarding against or allowing Bob to detect 1-bit errors. Now let's take a linear algebra perspective on this, because that's what the lecture is about. Let's say Alice's message is this. It's n-1 bits, so we can think of it as a vector in the field F2 of dimension n-1. And let G be this matrix, which is called the generator matrix for the code. And you see what happens is Alice transmits, I should actually say, well, okay. Alice transmits G times X. You see, if you do G times X, these first n-1 rows will just give you the copy of the message. And this last row means you add up all of the bits, right? That's like tacking on the parity bit. Okay, and then Bob will receive some version of this, y1 through n, possibly with 1 bit corrupted. So Alice has n-1 bit messages, but she's sending n-bit strings. Let C be the set of all strings that she might transmit. Then C is just the span of the columns of this matrix. Right? It's all linear combinations of the columns of this matrix. That's the set of n-bit strings she might send. So it's a subspace. It's an n-1 dimensional subspace of F2 to the n. Okay, so now imagine Bob receives Z1 through Zn. How does he do his check? Well, a linear algebra way to look at the check that he does, the check that he normally does is just add up all the bits he receives and see if it's 0, mod 2. So you can say he does it by multiplying this row matrix, which is called the parity check matrix, times the vector he receives. Okay, that really just adds up all the bits. And he checks to see if it's 0. If it's 0, then he detects that there's no errors. If it's 1, he detects that there's an error. Okay, same scenario, but I just did it with linear algebra language because we're going to generalize it. Okay, this solves the 1-bit error detection problem, but not the correction problem. Okay, it's a little trickier. Bob can sometimes know, oh, there's a mistake, but he doesn't know how to fix it. Okay, and we kind of prefer if he'd be able to fix it rather than, tell Alice, like, try transmitting again. So you see, if, say, Bob sees this string, 1 followed by a bunch of zeros, he knows there's an error because there's an odd number of 1s, but he doesn't know, like, was Alice trying to send the all zeros string and the first bit got flipped, or was she trying to send 1, 1, all zeros, and, like, the second bit got flipped, or what? Okay, so it's trickier to design a code that allows Bob to fix these bit flips. But the early pioneers of coding theory, like this guy, Richard Hamming, thought of some good solutions. So I'm going to tell you the simplest solution, which is called the Hamming 7-4 code. Okay? This is a code whereby Alice sends 4-bit messages by transmitting 7 bits. Okay? It looks a little specific, but there is a generalization. So basically, she has 4 bits, and she tacks on sort of 3 parity checks, and that helps Bob fix the errors. So the generator matrix for this code looks like this. Okay, so what does that mean? Alice has a 4-bit message, which we'll call x, a vector in F2 to the 4. And she encodes it for transmission by doing g times x, just like before. So she puts her x here, and she takes this linear combination of the columns, or she does this matrix vector multiplication. And actually, you see what happens. These first 4 rows, if you do this times this, you just get x1, and you get x2, x3, x4. So the first 4 bits she sends are just her message. But then she tacks on sort of 3 different parity checks, the sum of the last 3 bits, and x1 plus x3 plus x4, and also x1 plus x2 plus x4. Okay, so she's adding sort of more redundant information, which hopefully will help Bob correct the bit flip. Okay, so as I said, Alice encodes her string and transmits x followed by sort of 3 different parity check bits. Okay, so that's the G. Now, what does Bob do? I'm just going to tell you what Bob does. It looks a little mysterious, but you'll see how it works in the end. any code word y that Alice might send, anything that's of the form g times x, satisfies a bunch of parity checks. More than just, in the first case, the message always satisfied the check that the sum of all the bits was 0. There's some more checks that it satisfies here. In fact, if this H is this parity check matrix, I claim that whatever Alice transmits, if you multiply it by H, you get 0. So if Alice is sending this Y, oh, the laser's dead now. Anything that Alice sends of the form Y has the property that H times Y is 0, because Y will be G times X, and I claim that H times G as a matrix is 0. Okay, so H times Y, which is HGX, will just be the 0 matrix times something. Okay, and that's something that you can just check visually. H times G is 0. Okay, I mean, if you do the first row of H, dot all the columns of G, you get 0. And similarly for the second row of H times G and the third row of H times G. Okay, so we've cooked up these matrices. Alex is going to take her message X, send G times X. And we claim that whatever she transmits, Y, has the property that H times Y is 0. Any questions about that? Now, here's another thing I want you to notice. This H is not some random matrix. It's the numbers 1 through 7 written in binary. There they are. Okay, so Bob receives some strings, and let's call it Z. It's a 7-bit string. And first thing he wants to do is check if there is a corruption. So a natural thing for him to do is compute H times Z. Okay, on the theory that if there were no errors, he should see all zeros, like all 3 parity checks, like the sum of the last 4 bits should be 0, the sum of the second, third, 6th, and 7th bits should be 0 in Z, etc. As I said, if there are no errors, then Z is G times X for whatever Alice's message X is. So HZ is HGZ, which is the 0 vector. On the other hand, let's see what happens if there was one bit flip. If Z is formed by taking Y and flipping some bit. So if it's the jth coordinate that gets corrupted, then what that means is Z will actually be GX, the transmitted message, plus some vector that's all zeros except for a 1 in the jth coordinate, okay, which we call EJ. This just means the vector of all zeros, but there's a 1 in the jth coordinate. So that will be what Bob sees. And now if he does this parity check, H times Z, what will happen? H times Z is H times this thing, GX plus EJ. There's HGX plus HEI. HG is 0, so this part goes away. And what's left, the vector that Bob sees, is H times EJ. EJ is the vector of length 7 that has a 1 in the jth coordinate. So when you multiply that on the left by H, you just get the jth column of H, which is actually just the binary representation of the number J. So what this means is, Bob multiplies H times the thing he receives. If it's 0, he's like, great, there was no error. Otherwise, he gets like a 3-bit vector, which tells him exactly what coordinate the error was on. Okay, so that's a pretty cool scheme. Any questions about that? Okay, so Bob knows where the error is, and he can recover the message. Okay, that's great if you're sending like 4-bit messages. There's a generalization, luckily. For example, if you're sending 7-bit messages, there's a way Alice can do it by, this is rephrasing what happened. Alice can communicate one of 16 different messages, namely any 4-bit string, by transmitting 7 bits. And Bob can always fix one error. The scheme generalizes to the case where of transmitting any number which is like 1 less than a power of 2. In particular, for any value r, there is a scheme, I won't quite write it down, but H, again, has the property that's like an r by 2 to the r minus 1 matrix, the parity check matrix, where the columns are all the numbers written in binary. And there's some appropriate G that goes along with it, which has almost n columns, Okay, and the long and short of it is that Alice can send messages of this length, almost n minus log n basically. So she can send one of 2 to this, 2 to the n over n plus 1 different messages using n bits. So that's pretty effective. You know, she's using n bits to send one of almost 2 to the n different messages. And Bob can fix any error. And in fact, this is optimal for guarding against one error. So there's sort of a perfect scheme, like a most efficient perfect scheme, by which you can transmit n-bit messages and have Bob fix any 1-bit error. Okay. All right, so that's a nice application of linear algebra. And the last thing I want to tell you about in the remaining 13 minutes is quite different. It's about a problem from computational linear algebra, and I'm mostly just telling you this for fun. There's some aspects of this like you do not have to memorize for the test. You'll figure them out when you see them. Maybe you've even seen this before. So the question I want to end with is the discussion of how to algorithmically multiply two n by n matrices. At first, it doesn't look like a very interesting question. If you have two matrices, A and B, and you want to get C, you know the algorithm, right? I mean, you do like this row dot this column to get this entry, and this row dot this column to get this entry. Here's the formula. The ijth entry of C is like this dot product, the ith row of A and the jth column of B. And this is it, right? C has n squared entries. And for each one, you do it by dotting a row of A with a column of B, right? So basically, you have to do about like n or 2n work or something like that, something like n operations. So this algorithm takes n cubed operations, right? So to multiply matrices takes n cubed operations. So it would seem. Okay? It's hard to imagine any other way to multiply matrices. Yes, we're going to reduce the time complexity of that. Who's got, yeah, never mind. Okay, so actually, let's talk about a simple case, how to multiply two 2 by 2 matrices. Okay, we have A, B, C, D, E, F, G, and we want to get J, K, L, M. Well, this is how you do it, right? J is like A times E plus B times G, and there's similar formulas for the other 4 entries. And you see how many, I'm just going to count how many times we multiplied 2 numbers. Forget the additions. Here we did 2 multiplies, 2 more multiplies, 2 more, and 2 more. That's 8 multiplies. Okay? Now, if you think about this a little bit more, you'll see that actually, here's a different way you could do it. I will not make you confirm this, but you can actually get J as the sum of these 4 numbers, K is this thing, where like Q1 is this, Q2 is this, et cetera, et cetera, et cetera, et cetera. Okay? There's some crazy formula here. I assure you, if you expand it all out, it actually works. So what, you may say? Well, let me show you something. How many multiplications did you do for this computation? 1 for each of these Qs. 1, 2, 3, 4, 5, 6, 7. So if you really hate to multiply, you don't mind adding, but you hate to multiply, then you can actually do it with 7 multiplications. All right, that doesn't sound that impressive, but somebody probably has seen it before, like, now what can you do? No, you can't do 6. Actually, 7 is optimal. That's a good guess, though, whoever guessed it. Well, I'll tell you what you can do. Suppose you wanted now to go back and multiply 2 n by n matrices. Well, break them up into blocks, each of size n over 2. So it's actually still true that it works out. Like, you can get n by n matrix multiplication by doing it in these like 4 blocks of n by 2 matrices. So you can use exactly the same formula as this crazy formula before to get J, K, L, and M by doing these weird combinations of these submatrices. So before, we were multiplying numbers. These are numbers, but now these A, B, C, D up to H are matrices of size n over 2 by n over 2. But the formula still works. So what this means is you can do this whole calculation with 7 recursive calls to matrix multiply. Okay, these are all matrix multiplications. And that's a big savings. So if you imagine t of n is the time to do a matrix multiplication, this gives you like a recursive algorithm for doing matrix multiplication. Okay, do all the computations in this way and use recursion to compute these products. So this gives us a recurrence. To do matrix multiplication on n by n matrices, we need to do 7 matrix multiplies on n over 2 by n over 2 size matrices. And then there's about n squared work to like put them together, do the additions. Okay, because you have like n over 2 by n over 2 matrices that you got to like add up. So this is a recursion. And it's not too hard to solve it. And this is the solution. T of n is something like 7 to the log base 2 of n, which by elementary properties of log, you can interchange the 7 and the n. It's n to the log base 2 of 7. And that's like n to the 2.81, which is faster than n cubed. So that's kind of amazing. In fact, when this came out, like in 1969, the computer scientists were like, whoa. Because it's kind of stunning, right? I mean, it seems obvious that there's no other way to multiply matrices than, you know, do this formula, right, which takes n cubed steps. But like, here it is. Yeah, so that kind of blew some people's minds. This is due to Volker Strassen from 1969. This is him here. Actually, so Manuel Blum, who's a, you know, professor here, I mean, knew Volker Strassen back in the day, and he actually asked him, like, how'd you come up with this? And like the guy was like, you know, it's like trying small examples. You know, he's like, well, I thought about the 2 by 2 case. In fact, he even thought about the 2 by 2 case when the numbers were just bits, because then like addition is the same as subtraction. It's like really simple. And he's like, you know, I just tried to show like if you want to multiply 2 by 2 matrices together, you have to do 8 multiplications. And like I thought about it for a long time, and then I was like, well, actually you can do it with 7. So that's how we figured it out. Okay, and then I guess that was like a natural next step. Yeah, so he's a hero. In fact, also 2 years later with Schoenhagen, he showed that you can multiply, I kind of mentioned something like this before, you can multiply 2 n-bit numbers in time that's almost O of n. It's like O of n times some log factor. Which is also kind of amazing because if you think about the normal algorithm for multiplying 2 numbers, right? You have 2 n-bit numbers, and like you do the grade school thing. You kind of make this table with like n rows, each of length n. So it seems like it takes n squared time. He's like, no, you can do it in basically n order of n time. Also by some kind of recursive algorithm that like splits the numbers up into parts. Okay, so that was kind of awesome. So that was 1969. They figured out that you could multiply matrices faster than n cubed. It's like n to the 2.81. And it seemed like maybe n to the 2.81 is not going to be the fastest, right? Somebody suggested, hey, maybe you can do 6. No, but then you might think, well, maybe you can multiply like, you know, 6 by 6 matrices with fewer than, you know, 64 multiplications, right? And you can start playing around with ideas like that. And more sophisticated ideas can be used, and this is what happened. So actually, it took a long time to get this number improved. It was finally done by a guy called Pan. In 78, he got 2.796. And then the race was on. 2.78 by some Italian gentleman. Schoenhagen, like Strassen's buddy for integer multiplication, got n to the 2.5, which is pretty good. And then Romani was back. Then 2 heroes, Coppersmith and Winograd, beat n to the 2.5. And then Strassen was like, I got to get back in on this. So he got n to the 2.479. And then these guys made a big advance, Coppersmith and Winograd. It's n to the 2.376 in 1990. I don't know if you guys were born then. Probably not, right? Yeah, that was, and then like 20 years, nothing happened. So this is like a super famous number because there's like a million papers, research papers that are like, well, now we use matrix multiplication, so the running time of our algorithm is n to the 2.376. So, I mean, it came up in like many contexts. So it's important to try to improve this. But this was very hard paper, so they got stuck. Then something kind of amazing happened. There's a Scottish guy called Andrew Stothers, and in 2002, he beat it. He got 2.374. He wrote in his PhD thesis. But he didn't put it anywhere in his introduction or his abstract. He just casually mentioned it on page 81, in the middle of some computations, and you get into 2.374. And then he stopped doing math. He does business now. So literally nobody noticed except for the people that were on his PhD thesis committee. That's funny. And in particular, one person who didn't notice was Virgie Vasilevska, who was a PhD student here. She graduated in 2008. And yeah, without noticing, she also beat it, and she beat it a little bit better. She got 2.373. Yeah. That's it. That's the best algorithm known, n to the 2.373. So now, well, maybe there'll be more improvements, or maybe we'll get a million papers that include this as their running time. Yeah, so that's it. So this is a very, very famous problem in algorithms. It's getting closer and closer to n squared. And the dream, maybe, is that there's an O of n squared time for matrix multiplication. And can you get it lower than O of n squared? Can you get n to the 1.9? No, you cannot, because you have to write down the answer. Okay, and there are n squared numbers in the answer, and you have to write them all down. So n squared is the fastest you can do. Yeah, but so some people dream that you can get it down to n squared. Maybe you can't. That's a major research problem. Okay, that's it. Good luck on the midterm tomorrow.